Since electricity was first generated, scientists have been trying to explain its nature, and especially to identify the carrier of electricity, the particle we now know to be the electron. Now, in this program, we're going to start by looking at the contributions of three men: William Crookes, Robert Millikan, and above all, J.J. Thomson, who earned the title of discoverer of the electron. We've reconstructed in the studio a part of J.J. Thomson's lab, just as it was in Cambridge, in the Cavendish lab, in 1897. Now, let me show you one of his experiments. It's with this tube here. He called it a cathode ray tube. Now, I want to connect a high voltage to the tube from this rather interesting antique coil we've been making sparks with, so I'll just do that. Here we are. Right, now, we'll switch it on and see what we can see. Well, I don't suppose you can see very much with the lights on, so let's just turn the lights down a little bit. That's better. I'm sure you can see now that there's quite an impressive glow in the tube. But concentrate your attention on the bright patch at the far end on the screen. And watch what it does when I wave my little magic wand at it. Well, let's see what's going on inside the tube. The bright patch you saw was caused by a beam of electrons hitting a screen at the end. The screen's painted with phosphorescent paint, which glows when the electrons hit it. Now, where did the electrons come from? Well, they come from down here, where, as you can see, there's a little circular disc, a metal plate. That's called the cathode, by the way, hence cathode rays, and it's negatively charged. That's where the electrons are produced, and then they go through this electrode there. That's the anode, and you can see it's got a little hole in it, so they shoot right through the hole and all the way back down to the end of the tube. Now, why have a tube? Well, the tube, you see, has been evacuated. The air's been pumped out of it, because if there was air in the tube, the electrons wouldn't reach the screen. Now, I'd like to show you another kind of cathode ray tube. It's got a cathode, of course, as usual, and this time the anode is in the form of a metal cross, a Maltese cross. Now, let me just get some volts, 20th century volts this time, and connect it up like that. Well, I guess you can see something already, but maybe if we bring the lights down a bit, you'll be able to see it a bit better. There we are. Well, it does make a nice sharp shadow, doesn't it? Just as if the electron beam was traveling in straight lines for all the world like a beam of light. Unless, of course, I start mucking about with it with my magic wand again. Well, I've said that this is a beam of electrons, but can I prove it? Well, I suppose the first thing I can do is to use my magic wand. Because if we've got a beam of electrons here, I should be able to deflect it with a magnetic field. Now, in these cathode ray tubes, we're saying that what's flowing in here is a current, so it can also be deflected by a magnetic field. And we're also saying that it consists of electrons, of charged particles, a stream of charged particles. But are they really particles? Well, some 9 years before J.J. Thomson's famous experiment, William Crookes made this apparatus, which he thought showed that cathode rays really were little particles. Now, this is a cathode ray tube of the usual kind, with a cathode at one end, an anode at the other end. But this time, as you can see, there's a little paddle wheel in here, which can roll down two glass rails. Okay, now let's just turn the high voltage supply on for this thing. And we are. Let's see what it will do. There she goes. So it really does look as if the electrons are transferring momentum to the little paddle wheel, for all the world like this water jet. Well, if the cathode ray beam really is charged particles, there should be another way of deflecting it, in which we take advantage of the fact that a set of positive charges would attract a negatively charged beam, but repel a positively charged beam. So let's try and do that. Now, here we've got a tube which is sort of a more up-to-date version of J.J. Thomson's tube, and you can see it produces a nice, sharply focused spot. This is because it's got a proper electron gun back down here and a little bit of focusing. Now, since we want to deflect the beam with an electrostatic force, we've had to put a couple of plates here on the tube, and you can see the top one here is connected to the positive terminal of an electronic power supply, a high voltage supply. You can think of it as a stack of batteries, if you like, and the underneath electrode is connected to the negative terminal of the battery. Now, what I want you to do is to concentrate on the spot and ask yourself, which direction do you think it will move if the cathode rays carry a positive charge? Remember, the upper electrode is positively charged. Okay, let's turn on the voltage and see what happens. And turn up the volts. Hoopla. Well, that's clear enough, isn't it? Really does seem to show that the cathode ray beam, the electrons, carry a negative charge. But let's make absolutely sure, shall we? So what I'll do is I'll turn this off and swap round the two connections to the terminals. No. Right, let's turn it on again and turn up the voltage. There we go. Well, I think you'll agree that's pretty clear. It clearly shows that the electrons are negatively charged because this time, remember, we had the positively charged plate at the bottom, down there. So the spot always moves in the direction of the positively charged electrode. So electrons have a negative charge, but is there any evidence that they have a particular amount of charge?
One of the nicest pieces of information that we have comes from an experiment which was performed in 1909 by the physicist Robert Millikan. It's a very simple but clever little experiment, and he won a Nobel Prize for it. It was obvious to him that electrons were much too small to be seen. So instead of looking at the electrons themselves, he used small drops of oil. He produced a fine spray. And in the spray, the little drops get charged. In his experiment, Millikan put his oil drops between two plates, metal plates on which he was able to place electric charge. So let's see what happens if we put a charge drop between two charged plates. Now, to see the drops, we need some light. And I've got a television camera pointing in between the plates. Normally, I'd be looking at this with a microscope, but you want to see the drops too, so that's why I'm using a television camera and a big weight on top to hold it steady. The rest of the apparatus is a power supply to put an electric potential between the two plates, a switch, and in the top plate there's a small hole to get the drops in. Now, to prevent drafts, I have a chimney and a small device for closing the hole. Right, we're ready. The spray, open the hole and close it. Now watch what happens when I increase the potential. I'll switch it on now. Notice some of the drops are moving up. They're being attracted up towards the top plate. The force up is bigger than the force down. First, I'll pick out a suitable drop. That's provided by increasing and decreasing the voltage to get rid of all the other drops. Well, now I've selected one drop, and I'm going to adjust the voltage to keep it stationary. Increasing it now. Decreasing. And that seems to be about stationary now. Okay. So there's a downward force due to gravity, and there's an upward force, which is an electric force, because I've charged the plates. I want to keep that drop and change its charge. What I'm going to do is bombard it with electrons. It's already got a positive charge, and if I fire electrons at it, then it'll pick up electrons, and the charge will change. So to do that, I'm going to use a source of beta rays, which are just electrons. The dreaded strontium-90, an isotope of strontium that emits beta rays. And we put it in a little holder which points between the plates. There. When I open a little gate here, the beta rays will pass between the plates. Hopefully, some of them will hit the drop. But first, I have to switch off the potential. Otherwise, all the beta rays will be attracted towards one of the plates. When I switch off, the drop is going to start falling. So what I want to do is just get the drop up to the top of the screen so it's got plenty of room to fall in. Here we go. There, that's holding the drop fairly steady at the top of the screen. And now we switch off the potential and open the gate. Let's hope it's collected an electron this time. Getting near the bottom, so gate closed, potential on. It's still dropping, so I'll increase the potential. Get it up near the middle now. And we'll find what voltage we need to keep it steady. Well, that seems to be about it. Slight touch down, perhaps. Yes, I'd say that was steady. About 520 volts.
You've seen Charlie get two values of the voltage needed to balance the oil drop, to produce an electrostatic force in the upward direction just enough to balance the downward gravitational force on the drop. Now, it's quite a fiddly experiment, that Millikan experiment. I can remember when I was a student spending a week messing around with oil drops. Well, Charlie didn't spend altogether a week, but quite a bit of time getting a few more voltage readings, which you'll find in your broadcast notes. And what we'd like you to do with this is to take all those balancing voltages and see whether they're all consistent with the idea that the charge on the oil drop is just some whole number times a smallest possible charge, an elementary charge, in fact, the charge on the electron. Now, Millikan went further than this. He actually measured the charge on the electron. He did that by calculating the downward force on the drop that had to be balanced by his upward electrostatic force. So he found the electronic charge.